hoping to give you a few more hints to help you make sense out of Lab 3. And as I'm thinking about it, I believe it starts with an idea of encapsulation. This is not something we overtly explain very often because it becomes sort of obvious to us as we work through our careers in electrical engineering. We use encapsulation, but it's hard to go back and rewind and explain it. All right, so let me start with a simple example. Let's say that we had some function that we wanted to implement in a circuit, a logic function. All right, I'm going to put a box around it, and I'm going to say it has two inputs, A and B, and it has two outputs, X and Y. All right, it does some function. In this lab, we're going to have this do a couple of different functions. One is the half adder function, and the other is the full adder function. Okay, but for the purpose of this example, let's have it do sort of a nonsense function. All right, so maybe it'll take the A input and invert it to give you X, and then take the A input or that with B to get Y. Okay, so there's a circuit inside the box that builds the function. Okay, but you don't have to know exactly what's in the box as you start to use the function. So it's encapsulated. This shows additional levels of detail in the circuit diagram that perhaps cloud the issue and make it a little more confusing to look at. So you could replace this circuit with the function block. All right, so that way, if you wanted to connect several functions together, like we might have function, and one of the X and the Y inputs, you might want to do the function again. Okay, so it helps us understand the functionality, and you might have an input X and Y. They don't have to be the same, A and B. You know, it's a function that operates on signals. All right, but the idea here is inside the box, inside the function, is a circuit. All right, and so what we're going to get down to in this lab is using these functional blocks to represent simple processes. In our case, it's addition. And we'll learn how to put these blocks together to make something a little bigger. Okay, so we go from a half adder to a full adder to a 2-bit adder, and then in lab 4, we actually do, we change the circuit where it has the capability to do subtraction as well. Okay, so that's the first idea. All right, we want you to discover some things on your own. So I believe it's pretty straightforward to look at the truth table for a full adder. And so let's go through that real quickly. That's part of your pre-lab, but I don't think I'm giving much away if we talk about taking numbers A and B, representing those as bits, and coming up with a sum and a carry output. All right, so if I add, in this case, 0 plus 0, I get 0, and there's no carry out. So if I add 0 plus 1, the sum is 1, and the carry out is 0. 1 plus 0, 1, carry out 0. 1 plus 1 is 2, so that would be a 0 with a carry out of 1. That's the functional description in terms of the behavior from a truth table. All right, so let's move on. And you know, your job is to come up with a circuit. What goes inside the box that would give me this functional truth table? Okay, so then once we have that, we are going to build a full adder. All right, and so the full adder has slightly, a slight bit more capability. It's got a carry in input, so it's got 3 inputs and 2 outputs. And we know functionally, what that would do. This might have been the opposite order of your pre-lab. I don't remember. Let's see. Well, that's the way I set it up. Your pre-lab, you might look at it. Cn might be in the most significant bit position, but you'll get the point. Okay, so I now have 3 inputs, so I can go through all the input combinations. And I know what this is supposed to do, all right? I know it's supposed to give me a sum and a carry out. And if I said 0 plus 0 plus 0, that would be a sum of 0 with a carry out of 0. And so going through the table, you can go through that quickly. And when we get down here, 1 plus 1 is 0 with a carry out of 1. 1 plus 1 is, it's a 1 with a carry out of 1, binary 3. So you fill out this functional truth table and you know, oh, that's what a full adder is supposed to do. But then the question becomes, how do you build a full adder? What's the circuit that goes inside the box? All right, and so I think what's a little confusing about the way the lab is written, it's sort of mentioned in words that this is the setup that we're interested in for a full adder to be built out of half adders. So if you think about it, it makes some logical sense, but I don't know if it's easy to make that jump. All right, so if we think about it, what we're going to do is we're going to take the 2, he called them in the lab report least significant bits, so that would imply, I just now noticed this, I already worked up this truth table in the opposite order, but that would imply that the A and B are the least significant bits, so the order of the truth table should go AB with CI the most significant bit. Okay, sorry for that, but I have that a little bit different. But the idea here is you can add these numbers together. Get my eraser fixed. Okay, add these numbers together and you get a result. Then you take the carry in and you add those numbers together to get the next result. That's a natural way of combining half adders to get a full adder. All right, the question we're going to have is what to do with the carry bits. All right, and it turns out, I'm just going to give you the answer. It turns out that if you do an exclusive OR, that will work as the carry out bit. And so this circuit, everything inside the box, makes up the full adder. All right, and so your task, I just have to color this in because it looks unbalanced without the exclusive OR colored in. Okay, but your task is to verify that this full adder can be constructed from half adders and then use an exclusive OR on the carry bits. All right, and so when you do that, you'll be able to show, you look at the logic of the circuit and you'll be able to show it produces the same functional output that we wanted when we described the function of the full adder. Okay, so let's talk about how to do that. So what I have here is I have the first full adder highlighted in yellow. You can see the yellow box for the half adder. And then I took the 2 columns that are the input to the half adder and looked at the 2 columns that are the output of the half adder. So you see, that's not too hard to do. I'll make my pointer in red. 0 plus 0 is 0 with a carry out of 0. And you go through the truth table. 0 plus 0, 0 carry out of 0. So I left a few, I deleted a few of them, but you can check. 1 plus 0 is 1 with a carry out of 0. 1 plus 1 is 0 with a carry out of 1. So you see the yellow half adder produced columns C1 and S1, which I highlighted in blue and green. Okay, and just for the purpose of this video, I copied this truth table so I could carry some of the highlighting over. So same truth table, but this time we're going to take the other half adder, which I've shown in red, and we're going to look at those 2 columns. Again, it'll be blue and green. Okay, so because the S1 input is one of the inputs to the half adder, that's the column we care about. That's why I highlighted that in red, because that's one of the inputs to the half adder, to the red half adder. And the other input, you look here, it's Cn. So S1 is the input, Cn is the input. Now we do the half adder functionality. 0 plus 0 is 0 with the carry out of 0. 1 plus 0 is 1 with the carry out of 0. And so when you apply the inputs to the second half adder and do what the functional description of the half adder does, we know what that does, we can produce the columns C2 shown in blue and green. All right, then finally, S2 is connected in the circuit above to S. I didn't show that, but let me go ahead and show it. Here's S. All right, and so that's what this column would be. And then C out is the exclusive OR of C1 and C2. And so you can verify that. So, and then the last stage, to tie it all together, you would need to check this. Does this produce the functional description of the full adder? Okay, and of course it's supposed to. All right, so once you've done that, the next thing is we're going to put together two full adders. What we need to do is put together two full adders to get a 2-bit adder. All right, so let's let two of the switches on the digital trainer represent the A input. All right, so you would need to call this one maybe A1 and this one A0, this one B1 and B0. So we flip these switches and we can make like a 0, 1 plus a 1, 1, add those together and look at the outputs. All right, so you connect those to switches. All right, so I have these labeled here, so it gets confusing to see wires drawn all over the page. So if I have this labeled, I know that this goes right here. Okay, let me do that with color so you can see it in the video. If this is labeled yellow, I put it right here. Okay, similarly for all the other inputs. All right, so we connect the bits to the full adders, and then we take the outputs and we have to worry about the carries. All right, so the carry out of one stage goes to the carry in of the other. All right, so think of it, what we're doing is we're adding numbers together. All right, so 0, 1 plus 0, 1. 1 plus 1 is 0, carry out. 1 plus 0 plus 0 in the full adder would give me a 1 with a carry out of 0. So it's just like binary addition, all right, only we're doing it with circuits. All right, so the output should show up on S0, S1, and C out. All right, and what would make sense is to connect these in an order that makes sense visually. So I would want the most significant bit going to the most significant bit position on the LEDs. All right, so S1 would be connected to this LED, S0, I got that wrong, hang on, S1 would go here, S0 would go here, and the carry out is the most significant bit, that would go here. Okay, all right, so that gives you an idea of what to do in Lab 3. Hopefully you can complete these truth tables and come in with an understanding of how you're going to wire up these circuits. In your circuit diagrams, you have to replace what's in the box with the actual circuit. All right, so it asks for those two different things on the sign-off sheet where you have the functional diagram of the system. That's what this is. This is a functional diagram of the 2-bit adder. And then we want the schematic where you actually draw the circuit and you put dotted lines or something to show where the boundaries of the functional blocks would be. All right, so hopefully that will help you.